recording for folks who may not be able to join us. And that means I also need to turn on the transcript thingy and then consequently hide it from myself so I don't lose my mind. And there we go. Okay, no questions right now? No. So homework 3 is due Monday. So you got a few more days to work on it. Office hours as usual today. If you want to come hang out and work on it, that's perfectly fine with me. Any other questions or things you want to talk about before we dive into stuff? Everyone's quiet today. Is it that kind of day? It's a quiet, reflective kind of day. I can live with that. I can live with that. Can we play the what do you remember from last time game? I remove all these things so that you can't cheat and look at my screen. You are welcome. What do you remember from last time? So you could do gestures. This is totally a gestures question. In this case. There's one. Yeah. Bendy lines that look like Tinker Toys, right? Things stuck together. Correctly coding different slopes. Yeah, we're talking about what I would call piecewise slopes models, also known as linear splines. The idea that you would take the total amount of time over which you've observed an outcome and carve it up into sections that are consistent with different manipulations, different circumstances, the introduction of some kind of intervention or change in procedure, something like that. That's the type of situation that these models are designed for. And there are two different ways to set up the model. We had been through an example that has one of them so far. The easiest way to approach the problem is to create predictors that directly represent the rate of change during each period. And so long as you have more than 2 occasions, each of those predictors could also have linear and quadratic components. So you could have a section of time that has a bendy line to it as opposed to a straight line. And that will directly tell you whether or not there is change, say, during the first period, change during the next period. For more complex functions, you could also ask if there's an acute difference in an intercept. It takes more occasions usually to parse that apart, but that's another option. So that was the version we were talking about. The other version that we get to talk about today is changing the parameterization of the model so that it tells you about the difference in slopes instead. And that is more useful if you are studying a phenomenon in which change would be expected during each of the periods anyway, and what you want to know is differential change after some point. So I'll show you how to get those as well. Homework 4, for those of you who are feeling ambitious, is available and is a piecewise model. I'm asking to do the direct version of the slopes in that model, and that will be due in a couple weeks, so plenty of time on that. All right. Questions or comments on that before we dive back in? No, and I just realized I left my window open, so I'm going to shut it so that I'm not like black against the background. 1 second. There we go. That should be a little bit better. All right, then let's go to 6B. Let's see, which one is this? Is that it? Yep, here we go. I've got example 6B on tap here, and we were looking at fixed and random slopes. Do you want to go back through what we did before real quick? Would that be helpful to reorient us? Yeah. I'm assuming you don't have my handouts memorized. That's I don't either at this point, although some of them I've come close. I did just finish a new one this morning, so the next set of examples is ready for next week. 36-page handout, not my personal best, but close to it. This is what happens when you have 3 different programs and a bazillion estimate statements. So that'll be fun when we get there. Let's see here. We'll start from the beginning. Coding the slopes. There we go. So this is page 2 of example 6b. So we're still looking at the same data. We have 6 practice sessions over which older adults should be improving in their response time to a measure of simple processing speed. So we have balanced time in this case, which makes the coding of piecewise slopes direct and straightforward relative to unbalanced time. And I am setting up a model in which, let me see, let's get the picture out real quick. This picture? Yeah, this one. I'm setting up a model to capture change from session 1 to 2 as a distinct slope from the change from session 2 to 6. And I'm doing that entirely based on just the idea that I have a nonlinear trajectory and I think this is a reasonable way to capture it. As you recall, we looked at quadratic models before. They didn't fit very well, so I'm going to give this one a try. So this is the idea of what we're trying to do, is capture change from 1 to 2 and capture change from 2 to 6, each of which will have a linear slope. So I am creating 2 variables that look like this, and I have set session 1 as my intercept by giving each of my new predictors a 0 value at session 1. The orange variable then, my slope 1, 2 as I'm calling it, goes from 0 to 1, but then it shuts off at 1. And then the purple one, slope 2, 6 as I'm calling it, picks up where orange shut off to then capture the rest of the trajectory. So it's like one decrease and then a lesser decrease after that. So I started with a model in which I had both slopes in as fixed effects, so linear change during each period, and the only random effect that I had was an intercept. So this is a parallel change model. So we looked at that, putting slope 1, 2 and slope 2, 6 into the model as my new quantitative predictors. You can ask for predicted outcomes based on the model. So I have estimate statements in each of the programs that do that. And note the values of the time variable that for each of these slopes correspond exactly to the values in my coding table here. That's where they came from. So they should always match. And we looked at the results. At this point, we had significant change on average in our fixed effects. So from session 1 to 2, people improved about 163 milliseconds on average. After session 2, they improved about 33 milliseconds per session on average. And so then we added random slopes to that to be able to see to what extent each of those changes has individual differences. And one more piece of information that is useful to know is whether or not we have a difference in the slopes. So I tested via an estimate statement to what extent the slope at sessions 2 to 6 was different than the slope from 1 to 2. And the difference in those slopes is a coefficient of 130, meaning that the second slope is less negative by 130 milliseconds a session. And that is significant. So can you imagine a situation in which I would want to know this? What would be the utility of knowing that there's a significant difference in my slopes? Any ideas?
To know if the change in whatever you've done is having an impact.
Yeah, if the slopes are different, then that speaks to the effect of whatever manipulation or circumstance or whatever it was divided the two. In a more pragmatic level, this is how you answer reviewer 3's concern that you don't need a piecewise slopes model, that you could have just had one slope through the whole range of the data. If you can show that the two slopes differ from each other significantly, that speaks to the need to actually have this more complex function. So it is a useful thing to know. If this model gives me the change during each segment directly, then the difference in those rates of change is a linear combination that I can ask for. So this is what I call the direct slopes model, because each slope directly captures the change during each section of the trajectory. So then we had a random slope added to it. So we added U1 here effect for slope 1, 2 by adding slope 1, 2 to the random line. So I'm on page 5. Then we added slope 1, 2 after person idea here, data, as well as right here. And then if I add something random to the model, in general, folks, if I add anything to the model for the variance, how do I know if I need it? What's my procedure? Adding a new random effect. How do I know if it helped?
LR test.
Yeah, likelihood ratio test, my friend. So you can do this in SAS via my macro fit test that I wrote. You can do it in Stata via LR test as a command, and in R it is RANOVA. Not to be confused with ANOVA, which is a different thing. So I have an example of that in the code. Here's the results of my random, the first slope being random relative to only the intercept being random. Deviance difference here is the difference in -2 log likelihood. I've had several questions about this during office hours. When I ask for a test statistic from adding something random to the model, the difference in -2 log likelihood is the test statistic. That's one of the hardest words for me to say, test statistic. There's a lot of T's in there. And it is treated as a chi-square, test statistic. So in my write-ups, I have -2 and then a triangle for a change in log likelihood. You may also see that written as just chi-square because that is what that number is being treated as. So the difference in -2 log likelihoods, or what we call the deviance, is the test statistic. That tells us whether or not adding a random effect helped the model. So because we're adding things, the result of this significance test either says that it significantly helped the model or that it non-significantly helped the model. If you add things, it's better or not better. If you take away things, it's worse or not worse. So then we added the other random slope. So slope 2.6 shows up as a new random effect. And the key to getting the test statistic right in terms of degrees of freedom, because there's now 3 terms that are random, I have added 3 degrees of freedom to the model. So by adding a second random slope, I have added its variance, and I have added its covariance with the slope that was already there and the intercept that was already there. So that shows up there, that shows up here, it shows up over here in R. And so now I have a G matrix that's 3 by 3. So basically it's this last row that was added in this step. And another likelihood ratio test at the bottom of the page here. 3 degrees of freedom difference from the model, chi-square of 44, yes, it's significant. And then we did confidence intervals to give an effect size essentially for how wide the variation is in the units of the original variables. So these are in change in response time per session is the units that we're talking about here. And that was where we left off, if memory serves. Okay, so any questions on any of that before we go over some new stuff? No? We're good? There's one thumb. Thank you, Terry. All right. So then let's do that again. Second verse, same as the first. A little bit louder and a little bit worse. That's probably way past most of your time, but that's a saying I'm familiar with from my dad. So the same sequence of models using a different coding scheme. It tells us a slightly different take on the same information. So I would call this a re-parameterization. That's a mouthful. So I have changed which variable I am using to capture the change from session 1 to 2. So I'm picking up here with new stuff on page 9. I have a new variable that is just time for the orange part. And I have the same slope 2.6 for the purple part here. So I can think of this as time, or I can think of this as slope 1/6. The idea is that this orange variable by itself indicates the rate of change per session for all of the sessions. So like last week, we just called that linear time. It's still the same thing. But it changes its interpretation after we put in this purple variable. So think back to linear regression and the difference in what your slopes are if you have a predictor by itself versus if you have another predictor that's correlated with that predictor. The slopes go from bivariate relationships to unique relationships. Same here. So the purple part here is like after controlling for the overall rate of change, what is the difference? What is the unique aspect of what the purple variable here is capturing? And it's capturing change from sessions 2 to 6. So what ends up happening is that the second variable, slope 2/6, is how much different the slope is after session 2 than before. How much different it is what the purple variable, slope 2/6, is going to tell us this time. And the orange one, likewise, has to become the unique effect. And what orange has that purple doesn't is the change from sessions 1 to 2. So after both of these variables are put together in the model, the first variable, time, or slope 1/6, is going to capture just the change from session 1 to 2, and the purple slope 2/6 variable is going to capture the difference in change after session 2. So one would do it this way whenever you're in a situation in which change would be expected the entire time, and what you want to know is if the slope has changed from what it was before. Not whether there is change after session 2, but whether there is different change after session 2. So then all of the steps that we do to generate predicted values, for instance, are based on a different coding scheme. So different numbers go in here for what the value of the predictor would be at each of these occasions. We end up with our random intercept model to start with. And here are the coefficients. So the first two were exactly what we found in the previous model. This piecewise slopes model predicts that at session 1, which is when both of these predictor variables are coded 0, people take an average of 1961 milliseconds to do this task. The time variable is now the unique change from session 1 to 2. That's minus 163, same as it was before. And what used to be minus 33 here is now 130, because after session 2, the rate of change becomes less negative. And so then I can use an estimate statement to then put them together to get what the model says the rate of change actually is after session 2. So previously I had the first slope and the second slope. Now I have the first slope and the difference between the two as model parameters. They are equivalent though. You can get from one to the other. They are equivalent with respect to their fixed effects. Okay, how are we doing?
So for this second method, I might be overthinking, but VIF are fine because technically two slopes now, like because you coded 0, 1, 2, 3, 4, 5, 6. 6? No, we don't have 6, but like a 0, and then like a second slope 0, 0, 1, 2, 3, 4, 5. So they are highly correlated, right?
Mm-hmm.
So then collinearity wouldn't be messed up in this model?
No. I mean, they are going to be related, and the standard errors accurately reflect the extent to which they're related, but they have unique effects in the model that become exactly what I want them to be. And the standard errors are the same if you estimate the two slopes directly than if you do it this way to get one slope and the difference to get to the other.
I see. Okay, great. Thank you.
Other questions? So I have a picture here as to what the model is predicting. And I have the two equations side by side in terms of how they work. The first model that we used was the direct slopes, which is on the bottom. And we had the fixed intercept at the beginning, the rate of change from 1 to 2, and the rate of change from 2 to 6 is the minus 33. What we have now instead is the difference in the rate of change from 2 to 6 as the second model parameter. So each model can give us 2 out of the 3 terms that we might be interested in with respect to the slopes and the difference between them. And you could have set it up the other way, where the model gave you the rate of change from 2 to 6 directly and the difference in the rate of change from 1 to 2. You could have coded it the other way too. So then we can go through the same process of adding random effects, but this intermediate model in which only the first slope is random is not equivalent. So by adding only a random effect to the time variable here, on the model for the variance side, it's the same as a random linear time model. So the V matrix that we end up with has that same quadratically changing variance pattern as if we had a random linear model, because functionally speaking, that's what we have. We would add the likelihood ratio test to see if it helped. Yes, it did. We can then test the second random slope and see if that helps. And once we have both of them in the model for the variance, the interpretation on the random side matches the fixed side. So after controlling for random slope 2, 6, the variance of the first slope is just individual differences in the rate of change from session 1 to 2. The variance of the second slope is individual differences in the difference in the rate of change. But at this point, the two models that each have 2 random slopes in them are equivalent. So they would fit the same in terms of the 2 direct slopes model versus the slope and different slope model, because all of the effects that we have both fixed and random components to them. And this one also significant. And here are the confidence intervals for that. So just 2 different ways of asking for piecewise slopes. Either change during each phase directly, or change during one of the phases and the difference in change for the other. You can take your pick as to what's more useful to you in practice. Okay. All right. So how did we do? Is this good enough? And I did decide in homework 4 to let you practice this, by the way. So we'll go over this to make sure that everybody feels comfortable in doing these sorts of model comparisons. So here are the 3 models so far that we've considered in terms of what is a reasonable thing to do to predict change over time. The first part of this plot is the mean response time. So the black line with the squares, that's the right answer. That's from the saturated means model, in which I have 6 parameters that perfectly recreate those 6 means. The line with the diamonds through it that looks like this U shape, that was the best fit from the random quadratic model. And I have forecasted what each of these models says would happen to response time after session 6 to make the point as sort of like theoretically what process they're specifying here. And then now to compare it, we have our piecewise model. So it doesn't matter if you take the direct slopes model or the difference slopes model, because they're equivalent. They both have the same predicted response time at each occasion. So we have the circles here, and that circle line does a pretty good job relative to the saturated means. It predicts that response time is expected to continue to linearly decline, though, after session 6. So the second piece here would keep going indefinitely according to the model. So that's not too bad. What do you think? Good enough? Looks that way. But how can I come up with an empirical way of saying good enough? Any ideas? Let me phrase it differently. How many parameters did I spend in the model for the means to capture this trajectory with my 2 slopes? I have 1 intercept and 2 slopes. That's 3, right? How many possible? How many occasions am I trying to capture with my 3 fixed effects? 6. So I have 3 degrees of freedom left on the table. So what I'm going to do, thank you for the text, is test this model against the saturated model, not using a likelihood ratio test though, because we're in REML and that's not allowed, but by adding in the missing degrees of freedom and seeing if they help the model. So I did this in the polynomial example, and I'm going to do it again, just with one small catch in terms of which degrees of freedom, which individual session parameters I can add. From 1 to 2, I don't have any degrees of freedom. They're all from 2 to 6. So in terms of adding in session-specific dummy codes as new fixed effects, I am going to have to use the ones after session 2. Otherwise, it won't work. So I'm going to do that first, and then we'll come back to the model for the variance. So let me scroll back to the beginning of this handout where I made the dummy codes in the first place for just a second. What I'm talking about is this right here. So ahead of time, I had created 3 dummy codes for sessions 4, 5, and 6. In this model, it has to be after session 2 because the change from session 1 to 2 is already saturated by giving it its own slope. And I need 3 because I have spent 3 fixed effects and I've got 3 remaining. So I'm going to put in these 3 new predictors as fixed effects and see if they help the model. That's my plan. So this is, here we go. This is page 15. So in each of my syntaxes, I've added S4, S5, and S6 as new fixed effects. So they show up on the model line in SAS. They show up as C dot parameters in Stata. And they show up in the formula along with sloped 1, 2, and 2, 6. So if my model fits, if my 2 slopes do a good enough job at recreating the means, what should happen when I add these to the model? Do you think they should help or should they not help? No difference. Is 1 vote? Anyone else want to vote? Not help? There's another vote for not help? Yeah. If my model is good enough, adding stuff to it should not make it better. There is a saying, if it ain't broke, don't fix it. That is a very useful saying to apply to a lot of things in academia, because you can make yourself crazy trying to make everything perfect. But if it ain't broke, don't fix it. We're going to find out if it's broke by trying to fix it and seeing if it helps. So in order to test those new components, I need to ask for each program to lump them together and to give me a joint hypothesis test, what I would call a multivariate walled test, but we're using an F instead of a chi-square. So that's what contrast does in SAS, test does in Stata, and contest MD does in R. So in terms of the logic, what I'm asking for is to take the 3 fixed slopes that I've added and test their significance as a set. So it's the same idea as the F-test for a regression model. If these were the only 3 slopes that were in the model, it's, in this context, exactly the same thing as asking if the model R² increases significantly by adding these 3 new things. So like in a stepwise regression kind of idea, I'm testing the change in R². I'm asking for a contrast that does that test for me. I'm adding actually the chi-square option in SAS so that the comparison is on the same scale as the chi-square result that we'll get from likelihood ratio tests. So I'm lumping each of these 3 new contrasts together via each of these methods. So take a moment to stare at your program of choice and see if it makes sense the way that it's specified, or if I can help you figure out why it looks the way that it does. R being the most convoluted looking. But the reason there's so many more values in the contest MD statement is that you have to tell it what to do with each of the fixed effects in the model. So in contest MD, the first 3 are zeroed out because I'm like, no, leave those ones in. I want you to do this one, and this one. Okay, we good then? All right, survey says, pay no attention to the individual parameters. They don't have the same interpretations anymore, and we don't really need to know what they are. The only thing we're interested in is this joint hypothesis test of the 3 new terms. So survey says, no matter whether you treat it as a chi-square or as an F, doesn't help. So is this good news? Yeah. I win. It fits. It's completely atheoretical and made up because nothing special happened at session 2, but it fits. So note the correspondence between these things here. If I take my F and multiply it by numerator degrees of freedom, I get a chi-square. So it's the same thing either way. The difference is whether or not the test distribution uses denominator degrees of freedom. Now the variance side, because I'm only half done, right? My model has 2 sides to it. What I have just found out is that my 2 fixed slopes have accurately recreated the pattern of mean change. The other half of the model is still waiting though. How did my model for the variance do? Have I accurately recreated the overall variances and covariances for each occasion? So I have a visual of that I've made for the variances. The second half of the picture here on page 14. So again, the black line with the squares is the right answer. For the model for the variance, the right answer is from an unstructured matrix in which each variance and covariance gets to be whatever it wants. So I could have put the covariances in a picture here, but I didn't want to. So just looking at the change in the variance over time, here are the candidate models that we've examined. So random quadratic was relatively best fitting from the previous set of models. It improved over random linear, and it predicts this crazy quartic pattern of change over time because time to the 4th is involved in the predicted variance at each occasion. We have this thing that looks like an L. That looks kind of crazy with the X's. That's what happens if I were to let only the first piece be random but not the second. We looked at this on Tuesday and called it like half compound symmetry. Because yeah, a random slope lets variance change over time. The exact pattern of that change depends on what kind of random slope it is. If it's a random linear slope, variance changes quadratically over time. If it's a random quadratic slope, variance changes quartically over time. I'm sticking with it. I need an adverb in that sentence. And if I have only one of my slopes random, then variance changes quadratically during that section only. And so putting the two together, my random slope 1, 2, random slope 2, 6 model gives me this overall curve that looks kind of quadratic, but actually it's two different kinds of quadratic because it's two different sets of random slopes. So this looks pretty good, right? It's not terrible. It looks plausible anyway. So I need to do a model comparison because this is the model for the variance. Because I'm in REML though, I have to make sure that the model for the means is the same in both models I'm going to compare. So what I'm going to do is estimate one more model to serve as a comparison. I'm going to pit my random two-slope model against this kind of hybrid model here. So this is, I think, the last page. Yeah, page 16. I am using an unstructured R matrix, but I am keeping the fixed slopes in the model for the means. So the model to be compared is the fixed slope model with random slopes against the fixed slope model with an unstructured matrix. So conceptually, it's the same idea as adding in those dummy codes. I'm adding in extra parameters that would saturate the variance covariance matrix over time. And I'm asking whether or not that saturated unstructured matrix fits better than what this model predicts. So then we just have our standard likelihood ratio test against the best fitting piecewise model to this one that has unstructured variance instead. And in R, I had to do an extra step. So one of the things that I've learned about model comparisons in R is that they do not play across packages. So NLME is an R package that has GLS and LME, and those are the models that allow you to have some kind of level 1 R matrix, either an R-only model or a residual R matrix, whereas Elmer, which is from the LME4 package, does not. So in order to get a likelihood ratio test done by R, I had to re-estimate my random piecewise model in LME so that I can compare it to the unstructured model estimated in GLS, because those are within the same package, and then I could do not RUNOVA, but UNOVA, which is what that package uses. So this is to say that if you want to use R, you have to work a little bit harder to get this extra piece of information. But hey, it's free, right? And this is the part where I say you get what you pay for. That's another saying my dad would always say, you get what you pay for. So how did we do? Our likelihood ratio test is not significant. Hooray or boo? Thumbs up for hooray, thumbs down or sad face for boo. Yeah, hooray. What this non-significant result is saying is that letting everything be what it wants in terms of the variances and covariances didn't help. It's not better if I tried to fix it. So the extra 14 parameters that it would have taken to let all the variances and covariances be what they want did not help. Therefore, my model's good enough. So this is a candidate in terms of things I could carry forward to add predictors to. So let's see. Yeah, Nikki's here. She's hidden, but she's here. I was talking to Nikki yesterday, and she was reminding me about my analogy about painting. We're still taping the walls. Okay, we have not started painting it. We are still sanding and taping the walls and taking the light switch covers off and all of that prep work. The end result of all of this process is having a room that is prepped to paint. The painting part is when we get to add predictors that you actually care about. The predictors that are supposed to explain why some people change differently over time. All of that has to come after this legwork to make sure that your model for change actually fits in the first place. Yes, she's still there. So this is good news. That means that this is a plausible model, even though it's theoretically unhappy. Okay, questions? Okay, so now you know enough to do all of your next homework 2. Homework 4, I should say. Also, is what I meant by 2. But the fact that I'm characterizing a learning curve that should eventually like slow down and hit some sort of asymptote with linear slopes is theoretically dissatisfying. So I wanted to give you a little bit about what an alternative would be that would be a little bit better, and then show you a way to estimate it more easily. So we've done with piecewise stuff. I have a note about, let's see, if you only have 3 occasions, then watch out for random slopes that imply compound symmetry the other part of the time. But I wanted to go to this slide right here. Other kinds of models. So there are like 8 million kinds of nonlinear models of change that are possible in life. Not all of them are easily estimated in SAS mixed or in any other kind of standard multivariate normal program. But you can write your model out in certain types of software and estimate it that way. So let me give you a couple other examples of a nonlinear model here, what I call a truly nonlinear model. So in the phrases like general linear model, generalized linear model, this class is general linear mixed models. The linear part, that word does not mean that you can only have linear slopes. That word linear means that the model is phrased as slope times variable plus slope times variables plus slope times variable, or what is known as linear in the parameters. I have a couple examples here of models that are not linear in the parameters. So here is a snapshot of response time to this task from one session over the 30 trials that people actually completed that I summarized via a session mean for each person. So technically speaking, I should have used a 3-level model for these data. I could have modeled each individual trial at level 1, nested within practice sessions at level 2, nested within people at level 3. But I thought maybe a 3-level model would not be a great place to start. Can I get a thumbs up on that? Thank you, Lisa, for not giving us a 3-level model as the first thing that we do. Yeah, see, I can resist. But yeah, it should have been a 3-level model. So I have the mean across people for each trial here with this crazy black line. It's response time data. It's noisy. It is what it is. And I have the fit to 3 different models here, one of which is a linear model. The red line is a quadratic model, so that's the predicted U shape here. Then I also have the green line, which is a latent version of a piecewise model, where I had it find where the breakpoint should be. So that where the break is between the 2 slopes itself was a model parameter in creating the green line, and it came up with the breakpoint that is somewhere between session 6 and session 7. The fourth one, I should say, the blue line, is the fit of what is probably theoretically the most plausible, which is what's known as a negative exponential curve. And it's negative in this case because the change is slowing down. Not because it's going down, but because it's slowing down. So this is an example of what I would call a truly nonlinear model. The version that I have here has 3 parameters to it. It is an asymptote, an amount, and a rate. So I have curves here that vary only in the parameter that I'm focusing on in each picture. So these are very prototypical learning type curves. Like you get faster as you do this task, but only up to a point. You hit some sort of theoretical asymptote where you could keep practicing, but you're not going to get any better. So these three curves here on slide 37, they differ in their asymptote. Their optimal level of ending performance basically at time equals infinity, where the first person has the highest asymptote, the last person has the lowest. But otherwise, their curves have the same shape to them. They can also differ in amount. So amount is the total difference from where you start to where your asymptote ends up. Amount can also be reparameterized to become an intercept. So these three curves have different total amounts of change. They end up at the same point, but the red line had to take more work to get there than the green line or the blue line. And then the third parameter is the nonlinear one. It's a rate. And in this picture down here, they all start at the same place. They all end up at the same place, but the blue line gets there faster, has a more negative rate of change, a stronger rate of improvement. And so fitting this type of model makes a lot of sense. Like this sort of corresponds to how we think about learning and change. It predicts that after some point, you're not going to get better at this task. You're not going to get worse, but you're not going to get better. The only catch is that it's actually nonlinear. So here's what it looks like. So this is slide, I don't know, I can't tell what slide it is. Sometimes my computer does that and I can't tell.
I think it's 38.
Thank you. Yeah, 38. Yeah, I can see what time it is, which is not helpful, but I want to see what slide it is. So the nonlinear part is right here. In the level 1 equation, it's an individual amount times E to the rate times time. So it violates that slope times variable plus slope times variable linear format. So it is a truly nonlinear model. You can't do this in mixed. Can't do it in Elmer either. So the only way that I know how to do it is using SAS NL mixed, which is basically just a built-in likelihood generator where you can write your own version of whatever model. And so I'm going to make a separate recording for those models in SAS because that's not something I'm going to ask you to do, and it's not something that I have in all the programs. But I wanted you to at least see this. So the nonlinear part here is in level 1, but level 2 looks awful similar to the rest of our models, right? We have 3 individual parameters. Rather than having an intercept as beta 0, I've phrased it as an asymptote. The red part is the fixed part for what happens on average, and the blue part is how far off your version of it is. So each of these individual parameters for an asymptote, an amount, and a rate can have a fixed part, which is the common average trajectory, and a random part, which is how far you differ from each of those parameters. I will tell you that this random rate parameter, this U2, I have never been able to get it to estimate in real data. Not once. It blows up. So these models are much more challenging to estimate, not only in terms of just finding software to do it in, but also in terms of the amount of data that's needed. Any random effect that's inside a nonlinear function is going to be harder for it to find. The ones that are outside the nonlinear function, like the amount and the asymptote, these two here, those are going to be easier to find. So, you might be saying to yourself, yeah, I don't want to do that, Lisa. Can you teach me how to cheat? Why, yes. Yes, I'd be happy to teach you how to cheat your way into a nonlinear function. Look at these pictures. Look at this blue line right here, for instance. Doesn't that look a lot like it's hitting an asymptote? Yeah, this looks exponentially to me. These are positive slopes rather than negative slopes, but it's the same kind of curve. Like here's You know, this red one looks a lot like the learning curve, where you improve a lot initially and then your rate of improvement dies off. I created these curves from log transforming time. It's a hack. Because once you log transform time, you end up with a exponential relationship between log transform time and your outcome. So what's happening under the scenes here is given by these bottom two pictures. The x-axis in these bottom two pictures is natural log time. And the black line shows what the model would predict if all I put in the model was a linear effect of that transform variable. It is linear with respect to log time. It works out to be exponential once you back translate into regular time. And you can take that exponential-ish kind of curve and you can speed it up or slow it down by adding a quadratic effect of log time. So this is a twist on a random quadratic model that is likely to make it more plausible for most kinds of data. The downside of said twist is, what the hell is log time? Because we're used to thinking about the change per session, but one session of log time could be 2 sessions of a regular time, or 3 or 4, depending on where you are on the curve. So it loses the interpretation in a traditional linear model sense, but it gains a plausibility. And this is not in my book, but it is going to be next time. So let me show you that real quick. Move out of the way, please. There we go. The other handout, 6D, cheating your way to truly nonlinear change with log time. So here's the magic. All programs have natural log built in as a function. It's either going to be the word log or ln. Like in Excel, it's ln. In SAS, it's log. So just check your documentation that it's not base 10, that you want natural log. And I'm using the same dummy codes as before. So I got log time, and Stata I have to build log time squared. Got my dummy codes. Same thing in R, it's just log and R. So stepping through 4 models: fixed linear log time, random linear log time, and then the quadratic versions with fixed and random effects. So log time is my predictor. If I put in a linear effective log time, then these are the values of time that correspond to each of my sessions. So I had to take the natural log of session to find out what the value of the predictor would be. So I had that in each of my programs here. V matrix is compound symmetry, because all I've got is a random intercept so far. And here's the result. Response time is predicted to decrease by 156 milliseconds per log time. That's what it means. Here's a picture. Damn. Does this work or what? The yellow line is the prediction from a linear effective log transform time after you unlog it, exponentiate it. I like unlog it better because that makes more sense to me. So that's not bad. This model says that everybody follows the same shape. It's a parallel lines model, so we can add a random effect, same as usual. So adding in a random effect of log time, seeing if that fits better. Log likelihood ratio test and the usual suspects. So scrolling, scrolling, scrolling. Here's my likelihood ratio test for that. Yes, indeed, it does fit better. Here's some effect sizes for that. Is this good enough? Since it does look like it's pretty plausible. In this case, I have to put in 4 dummy codes. I have session 1, 2, 3, and 4 dummy codes in to saturate the model to test whether or not this is good enough with respect to the fixed effects. Why do I have 4 this time and not 3? Why do I have 4 of them and not 3?
Because it's not dividing it up into the 2 segments like before.
Yeah, I still have 6 occasions, but how many parameters are in my model to account for change over those 6 occasions? It's 2. An intercept and log time, so I got 4 to fill in. So I have the same idea, lumping together the 4 new parameters, adding that as a test, joint hypothesis test. Survey says I win. Log time is good enough. Is it good enough on the variance side? I can do the same thing by comparing a model that has a fixed effective log time and an unstructured model for the variance to see if a random log time slope does a good enough job. Got to redo models in R to be able to do the comparison on this in the same package. Survey says wah wah. So no, variance side doesn't fit yet. Here's a comparison of what the unstructured model has with its variances at each occasion and what the random linear log time model has. It's kind of whiffing on the end. So I keep going. Because I'm interested in fitting a better model for the variance, a random effect, I'm going to have to add it as a fixed effect. So I'm adding log time squared as a fixed effect, and then I'm going to add it as a random effect. So then the same ideas that you had in your polynomials homework apply here. The predicted outcome at each occasion is a function of time and time squared. The predicted linear slope at each occasion is time multiplied by 2. Just that these time values look screwy because they're in log scale. So I can add the fixed effect and see what happens with that. The fixed effect, curiously enough, is significant. So it did actually improve my model, even though it didn't look like it fit that badly to begin with that. So then we have the random effect after this. Here's the green line versus the yellow line. So the green line is what we have now after adding a quadratic effective log time. Fits just a little bit better than the yellow one. And random quadratic log time as the last candidate. Added 3 parameters because it's random quadratic variance and it's covariance with the stuff that was already there. And then likelihood ratio test is significant, meaning it helped. Then we can do our process of testing against the means model, 3 degrees of freedom here. Still fits fine. Testing it on the variance side against unstructured. And it's non-significant, meaning I win. So at the end of the day, it looks like either, I have a comparison here, the piecewise model, where both slopes are random, is plausible for these data, as well as random quadratic log time. So I have the summary of all of the different comparisons that I did to test model fit for each of these candidates. On the mean side, I tested the fit against the saturated means by adding in the dummy codes. And so to put these on the same scale, I took the F and converted it into a chi-square by multiplying by the degrees of freedom. The variance side, these came from likelihood ratio tests against the unstructured model. And then down here I have all of the models re-estimated using maximum likelihood because the truly nonlinear model only can be done in maximum likelihood. NL mix doesn't have Rimmel. And so then I can do a comparison through those. So it looks like I've got 2 plausible models to play with in terms of moving on. But because log time is tricky to interpret, the examples I'm going to show you next week with predictors are going to just use regular quadratic time. And that's the end of the story. Hooray. So, big picture, approaching this in life. Step 1, make a picture. The idea of what is it that my model is trying to account for? The individual data can be very hard to see what the trends are, but making a picture of the means at each occasion, saturated means, that tells you the general type of shape of the trajectory. That information combined with information about your design should then point you in a direction in terms of which of these families of models is going to be useful. I would say that piecewise models, unless you want reviewer 3 to yell at you, should be used as sort of a last resort if you don't have a theoretical reason to have a breakpoint. You can expect pushback on that. Otherwise, if it's some kind of continuous change model, then any of these families you could turn to. Just keep in mind like what is expected to happen after the end of the study. If it's not really plausible, then that might not be a great fit. So at the beginning of next time, what my plan is to do a review. Sort of a flow chart of all the things, like when you first are handed a longitudinal data set, what do you do first? Then what do you do? Then what do you do? And that hopefully will get us ready to start actually painting next week, adding time invariant predictors. How's that sound? Yay! So, questions or comments on any of this? No, everyone's out of gas. Is that a fair assumption? That's a car analogy, by the way, not a statement of anyone's gastrointestinal issues. Like your car is out of gas. Yeah, mine too. I hear that. So I tell you what, I'll let you go a few minutes early so office hours can start now. Have a great weekend, and I hope to see you all next week. Thanks for joining us. Peace out, everybody.